Okay, so we have three classes left, and then the final. So we have today, which is antiderivatives, and then more antiderivatives, and then more antiderivatives. So we're pretty much at the threshold of getting into Cal 2 now. So I thought I would take some time to just discuss, where Cal 2 is going to lead. How many of you have to take Cal 2? Who does not need Cal 2? Okay, so don't ignore me, but because this will still be, some of this will still be on the final. Okay, so in Cal 1, this is a brand new marker. What the hell, man? These markers are terrible. Wow. Okay, let me try the blue one. There we go, that's a little better. Okay, so Cal 1, the main idea in Cal 1, there were a lot, but the main idea was that if you're given a function, some function of x, that we can go to any arbitrary point on that function. Let's just call that a. Go up to the function, take a look at that point, and find the slope of the tangent line at that point, which would have been the derivative of that function at a. And that slope can have a lot of different meanings. If this is time, and this is the distance something has traveled, then the slope of that line will be a rise over run, right? Slope is rise over run, so it somehow gives you some information about the distance over time at a specific point, which related to distance over time and speed or velocity, right? So in other words, we were able to get the velocity at an instant in time. So we could say how fast something was going at that instant, right? And that could be time versus distance. It could be time versus pressure. It doesn't matter, okay? But that was the main geometric result. Now, in Cal 2, what we're going to do is we're going to take a look at a function. Okay, we're going to only look at it on a closed interval, all right? Remember, this is just the main idea, right? There's a lot more that we did, optimization, related rates, everything else, but that ties into this, I think, the best. So we're going to look at a function on a closed interval. So between 2 points, let's call this A, let's call this B. And what we're going to be asking ourselves is whether or not it's possible to calculate the area underneath that curve, all right? Now what's strange about that is when it comes to calculating areas, we know the areas of certain objects, right? Like rectangles, length times width gives you the area. If it's a circle, pi r squared. But this region right here is not a rectangle or a circle. So it has some weird shape to it because of the function, right? So there's no like standard formula for this to calculate the area. But it turns out that we can do it, all right? We can do it. Over here, to find the instantaneous rate of change of this function at a specific point, in other words, velocity, right? To do that, we just had to be able to take the derivative of the function, right? And we learned all the different methods on how to take derivatives. Power rule, product rule, quotient rule, chain rule, and all that good stuff. So we needed derivatives to do this. Over here, in order to figure out that area, to do that, we're going to need to calculate or need to determine not the derivative, but something called the antiderivative. The antiderivative. So one way to kind of make the analogy of this is, let's say that we had a function here that gives you time, okay? But not time in distance, time in speed or velocity. So let's say that this function is telling you how fast you were going at every point in time, okay? At every point in time, how fast you were going. This is telling you at every point in time how far you had gone, right? If you have speed versus time, anyone have an idea of what that area would represent? Acceleration would be the second derivative. Okay, so we start with the distance function, take the derivative, we get the velocity function, take derivative of that, we get the acceleration function. But
distance covered?
Pardon?
Distance covered?
Yeah, this is going to give, this area would represent how far you went. So what it's doing is it's kind of adding up, right? Like if you have, let's just take like an infinitesimal little slice of this. Let's just look right here at this little tiny little sliver right there. We have an amount of time that went by, right? And we had the speed over that time. Yes? So let's say I went 50 miles per hour for 1 hour. How far did I go? 50 miles, right? So this is like the amount of time. And if you multiply that times the speed over that time, that's going to give you the distance. What we're doing is we're adding up all those things throughout the entire trip. All right? And that would give you, that area would represent the total distance traveled. Another analogy would be if this is like the force you're applying on an object and this is time, so it's measuring the force over time, then the area under the curve would represent the work done, the amount of work actually required. So work is a physics term, force times displacement. But there's meaning to it, okay? Geometrically, it's just the area. But when you apply it to different fields, that area has meaning, all right? So we need to be able to determine this thing called the antiderivative. What do you think antiderivative means? It's like the non-derivative, anti. Anti usually means like the opposite, right? Or something like that. So if the derivative is one thing, the anti...
Perpendicular to the derivative?
Geometrically, it's not going to represent something perpendicular. It's a good guess, but it's not. I'm asking mechanically what it is. If we're starting with a function, then we know the slope of the tangent line is taking the derivative, and I'm saying that if we start with the function and do something, calculate or determine this thing called the antiderivative, that we're going to be able to find the area. But what? Yeah, it's basically starting with, it's like we're going to start with the derivative and go backwards, all right? But we're not starting with derivative, we're going to just start with a function. So for example, if I just make this cosine x, right? We know the derivative of this. What's the derivative? Cal 1. Derivative of that is negative sine x. That's the derivative, right? But the antiderivative of this would be sine x. Because what you're saying is, act like this is the derivative of something. What is it the derivative of? And it's sine. Does that make sense? There's a distinction between those two. So basically what I'm telling you is that everything we've learned, we have to learn how to do it backwards. All right? And that is a very unfortunate thing because it's not easy to go backwards. All right? Let me continue showing you more things in Cal 2, and then we'll get into the antiderivatives. So we go and we look at areas, and then we say, okay, well, there's something else we can do. This one's kind of weird. Let me just show you with an animation. I think it'll be easiest if I just show you with an animation. Hold on, I'm trying to remember which... where's my... There we go, okay. So here's what we do. There we go. Okay, can you all see that? I'm going to just pull up a seat here. Okay, you see we have two functions here. And in Cal 2, we're going to want to know the area in between those, all right, which we can do still using antiderivatives. But then what we do is we say, imagine that region is sitting in three-dimensional space, okay? And then take that and wrap it around the x-axis, all right? And then what you get is this solid. Y'all see that, right? We got a solid. And if we look at it, it's not, you know, if you put your hand in there, it's not like a straight cylinder in there. It's got a little curve to it, right? And that's because that bottom function creates that kind of weird shape in there, right? So what do you think the question is? What's the volume of that object? Okay? Yeah. It seems like that might be difficult, but it turns out that the way to answer that question is you just need to be able to find antiderivatives. If you can find antiderivatives, you're in business. But you have to be able to do that part. All right? And then, let me see if there's anything else here. No. Yeah, that's good enough. So we do these things called, those are called volumes of solids of revolution. Okay, volumes of solids of revolution. And you don't have to, you can take a region, you can wrap it around the x-axis, but you can also wrap it around the y-axis, and you can wrap it around like arbitrary horizontal and vertical lines. So we spend time on that. And then we do something, well, related to that. I should just bring that back up real quick. We can not only ask what's the volume of this, we can also ask what's the surface area of it. So like if we had to paint the outside of it, how much area would that be? Those are two different things, right? Area. So we find a way of finding surface areas of objects, of solids. And then we do something different. We take a function like this, and we ask ourselves, if we were to take this function and take it off the page and straighten it out, right? Imagine this is like a rope, and straighten it out. How long is it? And we call that the arc length. So it'd be like the distance if you had to travel along that path. And again, to do that, we're going to have to be able to calculate antiderivatives, all right? And then there's other applications. And then after that, you get into Chapter 8, which is sequences and series. So if you look at Cal 2, big picture, you spend the first like quarter of the class, at least if you take it here, we spend the first quarter of the class, third of the class, just making sure you know how to find antiderivatives. And then once we get through that, then we start doing these applications, areas under curves, areas between curves, volumes of solids of revolution, surface areas of surfaces of solids of revolution, arc lengths, okay? And then there's other applications like finding the center of mass of something. You can do hydrostatic pressure. There's different applications that we can touch on. And then Chapter 8. Do y'all want to know anything about Chapter 8, or should I just, no?
Sure. Yes.
Yeah? Okay. So, Chapter 8, I can kind of blow you away a little bit here. So, how can I do it? All right, how do I do this? All right, let's just take a function here, f of x equals cosine x. All right, now this is just going to motivate the idea. I'm not going to get too deep into this, but this will motivate the idea. Let's say that you're looking at this function, f of x is cosine x. We all know that the cosine function looks like that, and then it comes backwards like this, right? So it turns out that if somebody gives you a function, doesn't matter what it is, right? As long as it behaves pretty nicely, it's continuous. So as nasty as this you want it to ever be, there is a way to approximate this function with a polynomial. So we know what polynomials are, right? They look like this. There's this thing called the Weierstrass theorem that says that if you're given a continuous function, you can always approximate it with a polynomial function. So over here, there's some polynomial that is a very good approximation of that function. And I'm going to help us figure it out right now. I'm going to actually show you how we could determine what it is, all right? And then I'll tell you why it's important. All right, so I would like to approximate this function with a polynomial. All right, so when you talk about polynomials, we have degrees, right? Like a 0-degree polynomial would be a constant function. A first-degree polynomial would be a line. Second degree would be quadratic. Third degree would be cubic. Fourth degree would be, right? So on and so forth. So let me see if I can come up with, let's just try a quadratic, okay? Let's just go for a quadratic. Can I approximate this function with a quadratic? I think you would agree with me. If I try and put a parabola here, it's not going to be very good, right? Because this doesn't look anything like a parabola. But let's just try and make it look good right here, like just on this little arc, okay? So I'm going to try and come up with a parabola. A parabola ax squared plus bx plus c that will approximate that function near 0. So I want it to look, my parabola to be pretty close to what this is doing right here. All right? So one thing I could ask myself is, all right, well, it would be nice if both of them give you the same value at 0. Would you agree with that? So do we know what f of 0 is? What's this function's value at 0? Cosine of 0, which is 1. And so it'd be really nice if I got the same thing over here, right? So let's do that. What is g of 0? G of 0 is c, right? And what do I want that to be? I want that to be 1. So that means the polynomial I'm using, I should make that c a 1. Agreed? Okay, so far here's where we are. I'll put a little star next to it every time I update it. ax squared plus bx plus 1. Okay, so the functions match at that value, right? That function both go through that point. What would be something else I might want to have in common? The what? X-intercepts, that would be an approach, yes. I could try that. Okay, so opening up and down, right? This one opens down. What does that have to do with in our calculus class?
Well, A has to be negative.
A would have to be negative, but in terms of calculus, opening down would be talking about what? What would we be looking at? The second derivative, right? We want our second derivative to be negative, right? Do y'all agree? Let's back up one step though, because we're already talking concavity. Would you agree with this? Right now these match at 0, right? Wouldn't it be nice if their derivatives matched at 0? Like the slope of the tangent line of this one matched the slope of the tangent line of that one? Right? That'd be pretty good, like, way to head with this. So what is the derivative of this function? Okay, so the derivative of that function is negative sine of x. All right, what is the derivative of that function at 0? So what's the derivative of this at 0? 0. So I really want the derivative of that function at 0 to be 0 also, so it would match this, right? So let's take the derivative. The derivative of this function is 2ax plus b. And what do I want this to be at 0? 0. So when I plug 0 into this, I get b, right? And what do I want that to be? I want that to be 0. So that means I need to let b be 0. Okay, so update my function. My function now looks like this. ax squared, what? That's gone, right? Plus 1. Okay, so now their first derivatives match, right? What would be next? Let's make their second derivatives match. So what's the second derivative of this function? Negative cosine x. Okay, what is the value of that second derivative if I plug 0 into it? Negative 1. So it would be really nice if the second derivative of that one matched that, right? Okay, so let's do our second derivative. Our second derivative of g would be, here's where we are, that's g, right? What's the first derivative? First derivative, well, you know, let me do the first derivative first. It's just 2ax, right? Plus, plus b, that's our first derivative. But b was what? 0, okay. So I'm working with this right now, taking the first derivative, I've got that. Now second derivative is is just 2a, and what do I want that to be? At 0, I want 2a to be equal to negative 1, right? Which means if I solve this right here, a has to be what? Negative a half. Okay? So here's what I've got. My g function, I'm going to put it right next to this one. My g of x function needs to be negative 1/2 x squared plus 1. Squared plus 1. This quadratic should be a decent approximation of this cosine function near 0. All right? You follow that? Okay, do we want their third derivatives to match? Well, here's the deal. We went with the what? Quadratic? So once we get to the third derivative, everything's gone, right? Like pretty much the x's we don't have control over anymore. All right, here's our second derivative, right? What would be the third derivative? 0. So we don't have any control over it anymore, right? So I know that the functions, they match at 0, the derivatives match at 0, and the second derivatives match at 0. Now how good of an approximation is this? Let's see. Wrong one.
Professor?
Yes.
So, sorry, I got a little lost when, so why is the second derivative of g of 0, why is it equal to negative 1?
Because that's what this cosine function, the second derivative of it at 0 is negative 1.
Okay.
So the second derivative of this, right, if you plug 0 into it, you get negative 1. And so I want that to match over there. Okay, you ready to see this? This is going to be pretty mind-blowing, I think, I hope. So what we're saying is that if I look at the cosine function, right? If I look at the cosine function and I try and approximate it with a quadratic, negative 1/2 x squared plus 1 should be decent, right? Okay, so right now the red is the cosine function. The black one is my approximation. Right now I'm just using 1, so I haven't put the minus 1/2 x squared in there. Do you all think that this black one is a good approximation? No, it sucks actually. But they match here, right? They match there? Okay, so let's see what happens if I put that negative 1/2 x squared in there. There it is. You see it? Right there? And it's really close in here, isn't it? It's really close. Really close. So we did a pretty good job, didn't we? By putting a quadratic in there. But why did I start with a quadratic? I just picked it, right? I just said, let's do a quadratic. Maybe we could have used a higher order polynomial. Maybe a third degree or a fourth degree. And we could have kept following the same procedure, couldn't we? Like let's say I wanted to do an 8th degree polynomial over here. G of x, when I started the problem, I said, look, I'm going to have something in front of x to the 8th, plus something in front of x to the 7th, plus something in front of x to the 6th, right? Da, da, da. And then couldn't we have gone through that same procedure and just kept on making all the derivatives match one another? Okay, I'm gonna show you what happens when we do that with the computer. You ready? So here's the next one. If I were to have done a 4th degree, look at, this is what I get. Okay, this was the parabola, okay? And this is the 4th degree polynomial. Do you see that it's a better approximation right in here? I'm getting more accurate, right? So why stop at 4th degree? Let's go to 6th. Well, there is a 5th degree also, but it turns out that when you do the 5th degree, you get 0. So we're going to wind up getting zeros in front of the 7 and the 5 and the 3 and the 1. So we don't have an x term, we don't have an x cubed term, we don't have an x to the 5th or an x to the 7th. And that happens because when we start taking derivatives of cosine, every time we get sine anywhere, we plug 0 and we get 0. So that's why it's killing off all those odd powers. So here's the 5th degree, which again, there's nothing. Here's the 6th degree. Just keep an eye on what happens to the black function. Okay. Shall I keep going? Is that not freaking amazing or what? Do you see what it's doing? It's basically forming itself onto the cosine function. And here's where we are now. I've actually gone out. I'm at the 22nd degree polynomial. I'm at a 22nd degree polynomial. All right? And notice something about this. Well, Chapter 8 is about what are called power series. So I start with the function, right? What I'm telling you is that you can rewrite this function as a series of powers of x, right? These are all powers of x. It is a series of power functions, a polynomial, all right? But here's the big thing in Chapter 8. It's this polynomial right here is going to be infinite. It's going to keep going and never stop. And so because it goes forever, what you get is the fact that, see, if I keep going, this is going to just, I mean, you can't even tell the difference between the two anymore, right? What happens is that this cosine function actually becomes defined as this thing, all of this. So you can rewrite cosine as 1 minus x squared over 2 plus x to the 4th over 24 minus blah, 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 all that forever, okay? Every function can be rewritten that way. So why would that be valuable? Well, if you're sitting in a physics class and you need to figure out what cosine of something is in an algebraic problem, you can just use that, and that approximation is pretty much good enough. Would you rather work with the cosine function, or would you rather work with the 1 minus x squared over 2? So for a lot of real-world problems, you only need the first few pieces of this. You don't need all infinitely many. You just need a few. And not only that, isn't this easier to differentiate? Like if I asked you to take derivative of that, right? Wouldn't you like to do that? Yes? And if I make this complicated, let's say this function is complicated, really nasty, and you don't want to take the derivative. If you come up with its power series, then it would be easy to differentiate. All right? One last thing I'll point out here. Do y'all recognize all the powers on this? All the powers on that are even, aren't they? And do you remember in pre-cal, you're taught that cosine is an even function? That's not because they just like the word even. It's because its power series has just even powers of x. And guess what sine's power series is? Just odd powers. Okay? So power series, when you go to your calculator, if you were to do it right now and you put cosine of 4 into your calculator has no idea what 4 is. What your calculator does is this. 1 minus 4 squared over 2 plus 4 to the 4th over 24. And it goes out a certain distance and stops. And that's that decimal answer it spits back to you. Okay? That's what's happening in your computer. So like, why are power series valuable? Because without them, our computers wouldn't be able to do cosine, tangent, all those trig functions, natural log, all those, your computer would not know what to do with the input. Okay? All right. Can I show you one last thing? Yes? Okay, thank you. One last thing with power series. Okay, so I'm just going to tell you this. Sine of x has a power series, all right? Here's what it is. It's 1 minus x cubed over 6 plus x to the 5th over 120, I believe, minus, and then it keeps going, all right? You just have to believe me on this, all right? Let me just, I think it's 120. I'm pretty sure it's 120. Hold on, let me do it real quick. 5 times 4, 20. Yeah, okay, 120. All right, so this is really cool. What's the derivative of sine? Cosine, right? So if I take derivative of this, what's the derivative of that? So take the derivative of sine of x. What's derivative of x? 1. Okay, now minus. Bring the 3 out. 3 and 6 becomes 1/2 x squared plus, okay, 5 comes out, reduce that, and if you do 5 over that, I believe you get 24. So you get x to the 4th over 24. And isn't that the series I just showed you? It is, right? That's the series I just showed you. So everything behaves the way that you would think it behaves. Yes?
I don't want to, would there be an, how would you do tan of x?
Tangent of x? Great question. So tangent of x would be this series divided by this series. So how would you do that? How would you divide this by this? You would have to do x minus x cubed over 6 plus x to the 5th over 120 divided by 1 minus 1/2 x squared plus x to the 4th over 24. But the problem is these are both infinite series. They go on forever. So you have to learn how to, we have to learn how to multiply and divide power series. In fact, I'm doing that with my class tomorrow in Cal 2. So this is like towards the end. But you asked, and it turns out that there's certain functions we just have a like a table that we use anytime we want to find the power series. Like sine, there's a table, you just go read it. Tangent is on that table. So is like e to the x, the common power series. All right? So, last one, I promise. Now I feel like I showed y'all this already. Telling y'all what e to the x was? Right? I feel like I showed you this. Did I not? Yeah, I think I did. So this is the power series for e to the x. And when you take the derivative of that power series, you get back exactly the same power series, which is exactly what it should do. The derivative of e to the x should be itself. All right, so there were two, there's like, no, I won't say that, okay. Trying to do calculus without power series, you're really limited on what you can do. Because what I'm telling you is any function you ever get, no matter how complicated, has a power series representation. And once you get it to a power series, like I said, everything you do is easier because you can take derivatives and antiderivatives of this very easily. All right? Now, getting to the point where you're ready to start working with this, and what makes Chapter 8 so difficult is that you have to, there's about 2 weeks of build-up just to get you to the point where you can start talking about this stuff. All right, so I hope that's kind of like Cal 2 in a nutshell, but we are going to now talk about what we want to do here, which is start introducing the idea of antiderivatives. So I have a definition here. Okay, this is a definition. A function, capital F, this is the first time I've used this, capital F, is called an antiderivative of little f on the interval I if the derivative of capital F is equal to the little f for all x in the interval. So let's take a look at an example over here. Let's go back to this one. Let's say we start with this function cosine x. And go ahead and just erase everything we just talked about with power series. Just throw all that out. We're starting new idea. I'm using cosine because it's just easy to work with. This is a function, right? Somebody give me an example of an antiderivative of this function. Sine x. Okay, do you all agree that this is true? Capital F is an antiderivative of that because if I take the derivative of capital F, I get little f, right? Is this pretty clear? I mean, now, is this the only antiderivative? Is there another function you can think of that when you take the derivative of it, you get cosine? Sine x plus 2. What do y'all think of that? Sine x plus 2, would that work? So what's going on when you add that 2? So that's one example. Another example would be capital F of x. We said sine x plus 2. Because when we take the derivative of that, you still get your cosine, right? But this just goes away, right? Derivative of 2 is 0. So with that argument, we could just keep coming up with examples all day long, couldn't we? Sine x plus 3, sine x plus 4, sine x minus 5, sine x minus a half, right? Any number, we could add any number out here, couldn't we? And we'd still have an antiderivative. And that would work for any function you ever think of. Adding the constant won't change the fact that it's an antiderivative. So we have a little notation for this. We say if f is an antiderivative of little f, then capital F of x plus c is the most general antiderivative of f, where here c is any constant. So if we go back to this problem and we ask ourselves, find the general antiderivative of this. Find the general antiderivative. You would write down capital F of x equals sine of x plus capital C. And it's understood then that can be any number, any real number you want. And that is the most general antiderivative. So the way you look at antiderivatives then, well, let me do that one in a second. Let me put this up here. Let's do another example. Changing the function to the function 2x. All right? What is the most general antiderivative of this? So you have to think, what do you take the derivative of to get this? X squared. But we could add any number to the outside of that and we would have the most general form, right? So this little illustration shows the connection between the function and its antiderivative. So we want to look at the antiderivative as a family of functions. So what I have graphed here in red is 2 times x. It's a straight line, right? The parabola is x squared plus a constant. And we know that that constant can be anything. So what happens to a parabola if you add a constant to it? It's either going to move this thing up or down, right? So we actually have, if we change the value of c, we can see I'm changing the value of c here. All it does is moves all of those up and down. But what I need you to see is that there's actually, it's the entire family of these, right? It's all of these here. And there's something that they all have in common. And I thought that was on, no, it's not there. Where is it? Show family. I don't know where it is. Oh, wait. There it is. Okay, I knew it was somewhere. Here we go. So what do all of those parabolas have in common? If I go to a certain point, right, give me an x value, and I go to any of the functions in the family, the slope of the tangent line is the same at that point. Do you all agree? Which means the derivative of this function at this point has a value, and it's equal to this and equal to that. So the derivative of this function is the same as this one, and this one, and this one, and this one, and this one. So that's why this is the general antiderivative is a family. They all have the property that when you take derivatives of them, they all have a common derivative. All right? Do y'all see it geometrically? Okay. So what are the things that you should know? What are the things, walking in right now, the things that you should know the antiderivative of without even having to think too hard? So let's see. If little f of x, let's go with something easy. E to the x. What would the general antiderivative of this be? E to the x? E to the x plus c. You must put plus c every single time. All right? I know some Cal 2 instructors will take off. They will say, like, no credit if you forget c. I'm not like that, but I do take points off. You have to remember it's plus c. Okay? We have a function. Here's its general antiderivative. Okay, someone give me another one you know. Cosine. Okay, so we did that one. Cosine x, the general antiderivative of that would be sine x plus c. Okay, let's keep going. Sine, okay, let's go with sine. So if little f of x is sine x, be real careful here. What is capital F of x? Negative cosine of x. Negative cosine of x plus c. So the antiderivative of e to the x is itself plus c. The antiderivative of cosine of x is sine of x plus c. But the antiderivative of sine x, you have to incorporate the little negative in there, because when you take derivative of cosine, you get a negative sign, and negative sign becomes positive. Yes? Plus c? Okay. Questions on that? What other ones? What's that? Secant squared. Okay, so that's kind of weird, but we're kind of using what we know already, right? We know secant squared x is the derivative of tangent. So the antiderivative of secant squared x is just tangent x plus c. And we could do this for all the trig functions that we know that we know the derivatives of. So what's another one that we... Secant x tangent x. If little f of x is secant x tangent x, the antiderivative of that would be what? Secant x plus c. So do you see that all I'm doing here, or all we're doing here, is using what we already know about derivatives to kind of figure out some antiderivatives that we kind of know now already, just walking in day one, right? Day one into this topic. Any others that you know?
1 or 2 radical x.
Okay, if you want to put that, we can do that. I mean, it's not, yeah, it's not trig, but okay, that is something that we did talk a lot about, and it's kind of burned into your brain. The antiderivative of this would be just root x plus c, right? Okay, I've got one for you. I've got one for you. We'll just keep filling these out. We could keep going with the trig ones, couldn't we? Okay, so how about this one? 1 over x. Natural log of x. Natural log of x. Because the derivative of natural log of x is 1 over x. Now, what you're going to find is that whenever we take the antiderivative 1 over x, we have to take the absolute value. And here's the reason why. Do you all agree that this function is defined, this function up here is defined both for positive and negative numbers? Yes? However, if we just put natural log of x here, what can you not plug in? Negative numbers. And you can't plug in 0 either into this. But the thing is, you can't plug 0 into that either. So we have to eliminate negatives. So what we do is we say, okay, this is valid for any x so long as we take the absolute value first so that we don't get a negative in there. Okay, any others? We already did e to the x, right? So what about this? We know the antiderivative of sine, right? We know the antiderivative of cosine. Do we know the antiderivative of tangent? No, we don't, right? Don't say secant squared x, because that's the derivative. I'm saying, do we know the antiderivative of this? We don't. We don't know that, right? We never took the derivative of something and got tangent x, did we? Now, would you like to know what it is? I can show you, I can tell you what it is. The antiderivative of that should be, hold on. Yeah, should be the natural log of the absolute value of secant x. What? Is that right? Plus c. Plus c. Is that right? How could we check? Take the derivative, and it better be tangent x. So let's try it. Let's take derivative of that. What's the derivative of natural log of something? 1 over secant x times, what's the derivative of secant x? Secant x tangent x. And what happens? Secants cancel, and you're left with tangent. Now, would you have known that had I not shown it to you? No. But this is a good example of just how complicated it might be to go backwards, right? It's not a very natural process to go from here to here. You can check that this does work, right? But how would we do that from here to here? And that's the trouble that we run into in Cal 2.
Is there any other?
Oh yeah, we can do, so tangent has an antiderivative. So does secant, so does cosecant, so does cotangent. Now, they're on a formula sheet, which when you get more, into Cal 2 more, we'll reference that. I believe I have it here. So in the book, there's common antiderivatives that we should know. That's kind of what I'm doing right here. So let's take a look at what the book has in it. Let's skip the first three here. 1 over x, what's its antiderivative? Natural log. Antiderivative e to the x? E to the x. They didn't put plus c here, but they're just giving a particular antiderivative, right? Antiderivative cosine is sine. Antiderivative of sine, negative cosine. So we did all those, right? Antiderivative of secant squared was tangent. Antiderivative of secant tangent was secant, right? Now these two come from when we were doing inverse trig functions. And we were taking derivatives of them, right? And I told you this one was going to come up quite a bit. So there it is. The derivative of arctangent of x is 1 over 1 plus x squared. So the antiderivative of this is that, right? And same with this. These two are going to appear in Cal 2 a lot. And these are hyperbolics. Ignore these. We didn't talk about hyperbolic functions. You will in Cal 2, but we're not talking about them here. Okay, so where are we? We can only really find antiderivatives right now if it's something we recognize from Cal 1, right? Right? Okay, so let's try something else. How about this example? What is the antiderivative of x to the fourth? My condolences, sir. What about an antiderivative here? So that is a fourth degree power function, right? What do we know? If that's the derivative of something, what power did it start at? Fifth power. So let's just write that down. This would be fifth power, but what's wrong with that, plus c? What's wrong with this? If I take derivative of this, the first thing that happens is the 5 comes out, right? So derivative of this is 5x to the fourth. We need it to just be x to the fourth. So how could, yeah, we could put a 1 over 5 in front of it. We could put a 1/5 in front of it. And now, if we take the derivative, 5 comes out, cancels with the 5, and we get this. Y'all see that? Would this work for pretty much any power of x? Let's see. If we did f of x was x to the 7th power, then what would the general antiderivative of that be? 1 over 8 x to the 8th. Because again, we know the power is going to have to be one more than that. And then when that power comes out, it's got to get killed off, right? So this should work. Check it, take the derivative, it works, right? That is the good news in Cal 2. If there's any good news about antiderivatives, it's that you can always check your answer, right? You get an answer, you say, I think this is the antiderivative. You just take the derivative of it, and you should get what you started with. If you don't, then something's wrong. Okay, any power of x, will this work for any power of x? Let's try another one. How about f of x equals 1 over x squared? So let me do this. Let me rewrite that as x to the negative 2. We agree that that's a power of x? Okay, let's think about the antiderivative. What would the power need to be? X to the negative 1. Because we know the power we're going to subtract when we take the derivative, right? Like here, the 8 became 7, we subtracted 1. 5 became 4, we subtracted 1. We want to be able to subtract 1 and get negative 2, which means we're going to have to start at negative 1. Right? But when we do that, the negative 1 is going to come out. And we don't want that negative 1 there, do we? We just want a 1 in front. So just put a negative 1 in front. Would you all agree?
Yes.
Okay. Now I'm going to do it a different way. I'm going to do 1 over negative 1. You're going to start to see a pattern forming here. Let's do another one. Little f of x is 1 over x to the 4th. That's the same as x to what power? Negative 4. So capital F of x, the antiderivative, I forgot plus c. Here, what can we say about the x, the power on the x? What's it going to need to be? Negative 3. And then out here, we know when we take derivative, that negative 3 is going to come out. We don't want that there, right? So what am I going to put out front? 1 over negative 3. Do y'all see the pattern in all of these? Whatever power's out here, we're doing 1 over it out front. Whatever power's out here, 1 over it in front. Whatever power's out here, 1 over it in front. Whatever power's out here, 1 over it in front. But what's the power? The power is always 1 more that, 1 more than that, 1 more than that, 1 more than that. So maybe we can come up with a general formula. If we have x to any power, right, then the antiderivative should be x to what power? N plus 1. We're going to add, sorry, I forgot plus c here again. We're going to add 1 to the power, right? But then we need that to go away when it comes out. So I'm going to put 1 over n plus 1 out here, and then plus c. So do you remember in Cal 1, yeah. Do you remember earlier this semester, we had a rule for taking the derivative of x to the n? What was the rule? It was n comes out, x to the n minus 1. That was what we called the power rule, right? That was one of the first rules we learned. I used Pascal's triangle to prove that rule was true. So this is the power rule, right, for derivatives. What do you think we call that? The power rule for antiderivatives, okay? It is a generalization of the power rule for finding antiderivatives. So this is going to be power rule for antiderivatives. Now, there is one problem with this formula. The formula will break down for one particular value of n. What value?
0.
Nope, it works for 0. Look at your formula. When would this formula not make sense? When n is negative 1. Right? Look, if n is negative 1, what happens here? You get division by 0, right? And so the formula does not work when n is negative 1. So I'm going to put a little asterisk, right? This is the little disclaimer at the bottom of the page that you don't read. Okay? This is only well, I'll just put n cannot be equal to negative 1 or else the formula doesn't work. But let's take a look at that. What would we actually be looking at if n was negative 1? That'd be x to the negative 1, which is 1 over x, but what? We already know the antiderivative of that. That's natural log of x. Right? So we have every possible n covered. So let me give you one more. See if you can find the antiderivative of this. Little f of x equals 1 over the 4th root of x cubed.
Will we use chain rule?
We're not taking a derivative.
Reverse chain?
Yeah.
Not yet. No reverse chain rule yet.
So it's the same thing as saying x to the negative 3/4, right?
This is the same as saying 1 over x to the 3/4, which is the same as x to the negative 3/4. That is correct, Jackson.
And then so you bring the negative x.
Now we can use this. Okay? Now we can. But the important thing is you have to first make it look like x to a power. You cannot leave it like this. Okay? You can't. You have to convert it to x to a power before you use the power rule. Can't be 1 over x to a power. It has to be x to a power. So according to the power rule, here's what I'm going to have. I'm going to have x to the n plus 1. So this plus 1, right? Negative 3/4 plus 1 over, in front, 1 over negative 3/4 plus 1. So I'm going to have to add those together, right? So negative 3/4 plus 1 is 1/4, right? 1/4. So continuing now, I have that capital F of x plus c. Capital F of x should be 1 over a 4th x to the 4th plus c. But what is 1 over a 4th? 4 x to the 1/4 plus c. Is it correct? Check it. Take the derivative. 1/4 comes down, hits the 4, it's gone. Right? Subtract 1. What's 1/4 take away 1? Negative 3/4. So you're going to wind up right there, which you could rewrite that way. All right? All right. It's almost fun. It's almost fun. Okay, how about this one? Little f of x is equal to 1. What's capital F of x? Just x. X plus c. Right? Because what's the derivative of x? 1. Right? The derivative of x is 1. All right. How about this one? What's the antiderivative of 5? 5x plus c. What's the antiderivative of any constant? That constant times x plus c. Right? All right, let's continue. This is fun. It is fun. Now I'm going to make it official. It is fun. Okay, what about this? Square root of x plus 1 over x. Find the antiderivative. So what's different about this problem? I've got addition between these two. Now, let me ask you. When we were taking derivatives, if we had addition, could we just do them separately? Yes, with addition and subtraction, right? We were allowed to. Well, good news. With antiderivatives, it works the same way. You can do them individually, all right? So the antiderivative of this, we might want to start by rewriting this as x to the half